Joke number one, chemistry is fun. No, about exams, they're graded, but they're sitting on my table at home. I'm sorry, I forgot to grab them on the way here. I know that you guys probably think that that's a lie, and most of you are probably right about that. But I'll get them to you next week on Tuesday, okay? And on that note, we're going to move forward. Just in review, so we're going to spend today talking about those phase diagrams that we looked at. When was the last time we talked about this stuff? It must have been last Thursday. So we had a diagram that we derived, or we looked at. It was kind of a function of the chemical potentials of substances, and we're looking at a single substance, and we're looking at the equilibrium between its solid, its liquid, and its gaseous phases. And we had something that looked like this. We had the gas phase, we had the liquid phase, and we had the solid phase. And we had pressure on the y-axis, and we had temperature on the x-axis. And we had an equation that said that mu, or mu is equal to the Gibbs free energy per mole, d mu for the substance was equal to V dP minus S dt, where V is the volume of the substance, and S was the entropy of the substance. So in this phase diagram, all of the lines were positions of temperature and pressure at which two phases would be in equilibrium. So if we move along this boundary between the solid and the gas, if we're at this particular temperature and this particular pressure, exactly right there, then our solid and our gas phases would be in equilibrium, right? Because this line is defined as the equilibrium line for these guys. So what happens if we're sitting at this particular pressure and this temperature, and we leave the pressure constant and we increase the temperature? So we leave pressure right here and we increase T from T1 to T2. We end up with a point over here, right? Is that a point of equilibrium?
Nope.
It's a point where the gas phase is favored over the solid phase, right? Only on the lines of that phase diagram are our substances in equilibrium. So we argued, what did we do? Let's go back and revisit everything. We argued that the gas phase would have a larger partial molar entropy, and so the slope, the Gibbs free energy with respect to temperature for the gas phase would be the largest slope. The liquid phase tends to have less disorder than the gas phase, and so it would have a slope that was less than the slope of the gas phase, and the solid phase had even less disorder, a lower entropy than the liquid or gas, and so its phase, or its slope, the slope of the Gibbs free energy of the solid with respect to temperature would be lower, right? And we kind of said that essentially we can look at this curve and decide based on which phase had the lowest Gibbs free energy, which would be favored at a particular value of temperature or pressure. And you see that as we move back to lower temperatures, the chemical potential, the Gibbs free energy, partial molar Gibbs free energy of the solid phase would be the lowest at low temperatures, and it would be the highest at high temperatures. Yeah? Or sorry, the solid would be the lowest at low temperatures, and the liquid would be the lowest at high temperatures. So or the gas actually down here would be the lowest at high temperatures, and the liquid would be lowest over here. Essentially what we're saying though is that as we increase the temperature, we end up favoring the phase with the largest amount of entropy, right? The largest amount of disorder. And as we lower the temperature, we end up favoring the phase with the most order, the least amount of disorder. We went from there. Oh yeah. So we went from there and we looked at the volumes and how the volume of the sample or of the phase affected the free energy. And we said that because the gas phase has the largest volume, again, it's going to have the plot of the chemical potential versus pressure is going to have the largest slope since the free energy depends on the volume times the differential change in pressure. And the liquid has generally the next smallest volume, and the solid has the next smallest volume. And so the slopes of those lines end up being less than that of the gas. And the suggestion then was that as we lower pressure, because the Gibbs free energy of the gas drops most rapidly with pressure, that the free energy of the gas is the lowest for low pressures. As pressure increases, Gibbs free energy of the gas spikes, and so it ends up being that the solid is the one with the lowest Gibbs free energy with high pressures. So we looked at it from that argument, just looking at plots of the Gibbs free energy. And then we also showed that if you take a given point on one of these equilibria curves, I think it was this guy that we used, we said that holding temperature constant and increasing the pressure will end up increasing the Gibbs free energies of these guys differently, right? The molar Gibbs free energy for the gas and the liquid and the solid are different because they have different volumes. And so a given change in pressure will elevate any of these curves at different rates. And depending on which curves are elevated the most or the least, our equilibria point will shift from one position to another. We saw that for water, an increase in pressure actually shifts the melting point temperature to lower temperatures, and that was because water had a negative molar volume. We saw that for most things, an increase in pressure shifts the melting point and the boiling point to higher temperatures. We did all of that essentially just looking at these diagrams. So what we're going to do today is we're going to make essentially all of the same arguments, but now using some math. And so we'll crank out that math and show you what it is, and then basically reach all of the same conclusions that we reached the first time, just via a slightly different route. Okay? But before we do that, I want to talk about what is suggested by these phase diagrams and what is the vapor pressure. So let's pick a point on one of these diagrams, possibly a liquid, let's take a liquid gas equilibrium. And let's ask ourselves what it means for the substance to be in equilibrium. for the liquid phase and the gas phases to be in equilibrium. So I'm going to draw a little piston because that's what we like to draw in thermodynamics classes. Pistons. I'm going to put a substance, liquid phase, the bottom of the piston, and I'm going to put a weight on it, weight on the piston. I'm going to push down with a pressure that's equal to the equilibrium pressure of that particular gas in equilibrium with its liquid. So at equilibria, essentially, the internal pressure of this gas is such that the rate of capture of gas molecules by the liquid is equal to the rate of departure. So there's something referred to as dynamic equilibrium. Essentially, at this surface between the liquid and the gas, you have an exchange of material. Nothing is necessarily constant. There's always movement from the liquid phase to the gas phase and from the gas phase to the liquid phase. But at a position of equilibria, the relative amounts of liquid and gas don't change, which means that, again, the rate of capture, K capture, is equal to K departure. And the equilibria pressure is defined as the pressure, the internal pressure of the gas requisite to be essentially forcing gas phase molecules back down into the liquid phase fast enough to replace their departure from the liquid phase to the gas phase. Yeah? And that's what each of these points along this liquid-gas equilibria curve represent. They say at a particular temperature, this body of liquid is going to have some amount of internal energy, and because it's got that internal thermal energy, it's kicking molecules off and into the gas phase at some particular rate. And if it's just allowed to simply do that, throw those gas molecules or those liquid molecules out in the gas phase, eventually all of the liquid will disappear. But if that gas is captured and pressure is allowed to build long enough, the pressure can build to a rate at which the rate of collisions and capture ends up being equal to the rate of departure, and then you have a dynamic equilibrium established. So what happens if I push on this piston with some pressure that's greater than the equilibria pressure of the gas, the equilibria vapor pressure of the gas at that temperature?
The rate of capture is going to exceed the rate of departure.
Rate of capture will exceed the rate of departure, and what will happen to the gas phase?
It's going to condense.
It'll all go to liquid. So if we're at a particular equilibrium point, and the internal pressure is exactly the right pressure to make capture departure rates equal, but we increase this pressure by shoving down on the piston, then as pressure increases from one particular point on the liquid gas equilibria curve, we move up into the area of the phase diagram where we're no longer at equilibria and the liquid phase is favored, right? So if P external here is greater than PQ, push that piston down. What happens if it's less than the equilibrium pressure?
Gas will push out
Yeah. How long will it push out?
until it reaches the pressure, the external pressure.
That's the thing. That's the kind of the point that we're trying to make, is that as long as that external pressure is less than the vapor pressure of that gas at that particular temperature, if we take this point and we say that the pressure is less than the equilibrium pressure, we move into this phase or the stage where the phase that's favored is gas. We're no longer at equilibrium. We're at a phase where the gas phase is favored. And so as long as that pressure is less than the equilibrium pressure, it's just going to keep pushing that piston back until eventually the piston flies off into outer space and all of that gas has had a chance to, or all of that liquid has had a chance to go gas phase. We only end up being able to trap it if we push back down on it with an external pressure that's equal to the vapor pressure of the gas, right? So anytime the pressure is less than the equilibrium vapor pressure, we favor the gas phase. Anytime the pressure, the vapor, the internal pressure is greater than the vapor pressure, we favor the liquid phase. Yeah? So what that means is that each of these values of P and T, and at any given value of P and T, the value of P is equal to the vapor pressure of the gas at that particular temperature. So the equilibrium vapor pressure of the gas at that temperature. All right, so now we do some math. And what we're trying to look at is we're defining a situation that we know must be true. If we're at a position on this curve, on any of these curves, on the solid gas boundary, the liquid gas boundary, or the solid to liquid boundary, if we're sitting directly on point on those lines, then we know that the chemical potentials of each phase are identical, that they're equal. If the chemical potentials weren't identical, then we wouldn't be in equilibrium. One phase would be favored over the other. Whichever phase had the lower chemical potential would be the favored phase. But along any of these curves, chemical potentials are equal. And so, if we want to trace movement from one point to another, say that we're moving from this point to this point on the curve, we know that as we increase temperature, to maintain equilibrium, we're going to have to increase the pressure by some amount. And the question is, by how much must we increase the pressure for a given increase in temperature? And we're going to try to express that mathematically. So we derived this equation that said dG was VdP minus SdT. And what we're going to say now is that for equilibria to remain equilibrium from one position to another, that the change in the Gibbs free energy of each phase must be equal. And so what that means, we write an expression that says that VdP of phase 1, so the molar volume of phase 1 times however much the pressure changes, the differential change in pressure, minus the molar entropy of that phase times the differential change in temperature, is going to be equal to dG of phase 2, which is the volume of that phase minus the partial molar entropy times differential change in temperature. So we set these two equal to each other, we group the terms that multiply the dt, whatever that thing's called, and the dp differential. And we get an expression that looks like this: S of phase 2 minus S of phase 1 times dt is equal to V of phase 2 minus V of phase 1 dp. S of phase 2 minus S of phase 1 for a transition where we go from phase 1 to phase 2 is just delta S of the transition. Same thing for the volume. V of phase 2 minus V of phase 1 is delta V of the transition. And we have this expression that says delta S transition dt is equal to delta V transition dp. So dp over dt is delta S over delta V. So what that's saying is that the slope along any of these curves, slope is the rate of change, it's dp over dt, how much does pressure change when temperature changes, is equal to the change in the entropy divided by the change in the volume. So let's talk about what that means for the magnitudes of these slopes. You can look at that equation and you can start talking about the size of that delta S term as you are sitting along any of these phase boundaries. What do you think about the relative size of delta? What do you suppose the relative sizes of delta S would be between a solid to liquid transition or a liquid to gas transition? Which one do you think would have the larger delta S, the solid to liquid or the liquid to gas?
Liquid to gas.
Yeah, liquid to gas.
Yeah, liquid to gas. We go into that large volume change. You're looking at a much larger change in the entropy. How about delta V, change in the volume? Liquid to gas is going to have the largest change in the volume. It turns out that it's the change in the volume that has the largest effect on the magnitudes of these slopes. So while we do expect that delta S is going to be, relatively large for a solid to gas or a liquid to gas transition, the slope of the solid gas line and the liquid gas line ends up being lower than the slope of the solid liquid line, even though these transitions have a larger delta S, because the delta V here is so much larger. So delta V for a liquid to gas transition or solid to gas transition is so significant that it ends up decreasing the slope of that thing relative to the slope of the solid to liquid transition. So we end up with a steep slope on that solid liquid curve. We end up with more shallow slopes on the liquid gas and the solid to gas transitions. Speaking of the solid to liquid transition for water, how can you argue for the slope of the solid to liquid boundary for a water phase diagram? First of all, when you look at this curve, how would you have to change this curve to make it resemble water's phase diagram? Water looks like that. The solid to liquid boundary for water has a negative slope, and that's because delta V for the water liquid to gas transition, or sorry, solid to liquid transition, ends up being negative. And so that guy water has a negative slope. What's my next thought? You can use that equation to make estimates of what the magnitudes of the changes in the slope are, or the differences in the slope are. It turns out that the slope of the solid to liquid boundary ends up being something on the order of 1,000 times larger than the slopes of the liquid to gas and the solid to gas boundary. I might get a chance to show you one of those equations, but I'm going to move to some other things first, and we'll double back if we have time. You can recast this equation. We said that for phase transitions, we have that delta S is equal to pressure process over T. ds is QP over T, and that is delta H over T. And so we can take that expression that we derived, dP over T is delta S of transition over delta V of transition, and we can turn that into the expression dP over dt is equal to delta H over T delta V. Generally, these terms, delta S, delta V, and delta H, are they functions of temperature? And pressure? Yeah. In general, all of those quantities, the enthalpy and the molar volume, are things that change as pressure and temperature change. And so if you want to solve these equations precisely, you have to factor in all of the relative changes in enthalpy and volume and entropy, etc., for a given change in temperature and pressure. But for certain movements within small kind of differentials of temperature and pressure, we can hold some of these things constant. And so that simplifies some math. Let's look at an example of that. Along the solid liquid curve, we have, write this expression as dP is equal to delta S of transition over delta V of the transition dt. And so integral of dP is equal to the integral of that guy, delta S over T. And we can replace delta S with delta H over T. Say that the integral of dP is equal to the integral of delta H over T dt. And if you assume that H is put that delta V in there. If you assume that delta H and delta V are not functions of temperature or pressure, you can pull those guys out of the integral. So we have the integral of dP is equal to delta H over delta V times the integral of dt over T. What's the integral of dt over T? So integral dP is P, evaluated from final to initial is P final minus P initial.